if it comes to be that methane-based life is possible, then it could be the case that because red dwarf stars are the most common types of stars, and because they're the longest lived stars, that methane-based life would potentially be the most abundant type of life in the universe, and we could actually be in the minority of life being water-based. Hello and welcome to Entropy Rising, where we talk about science and futurism. I'm your host, Jacob, and as always, I am joined with my wonderful co host, Lucas. Lucas, how are you doing today?
I'm doing great today, Jake. How are you?
I'm doing good. We're recording. I'm happy. The usual setup.
Yeah.
So, today we are going to be talking about the extreme places that we think we could potentially find life in the universe, specifically focusing on the places we wouldn't naturally think to look. These aren't going to be the ideal water based worlds in the habitable zone of a star like our own, but instead, these are going to be some extreme environments that I don't think most people would look for life. And we're going to talk about how it could exist there, anyways.
Yeah. It's a really interesting idea to think about where life can actually manifest and maintain itself out there in the galaxy and can actually help a lot of people to speculate how possible life really is out there.
Absolutely, because if we can expand our understanding of life and imagine these extreme places, then that just gives us more options and more opportunities to look for life in places that we wouldn't have considered.
Yeah, for sure.
So I feel like before we dive into some of these extreme examples, and we do have some pretty extreme examples that we're envisioning here, we should probably talk about how life got started on Earth and some of the extreme examples of life we see even on our own planet.
Yeah.
I tend to believe that at least basic life, that single cellular life, is probably very common in the universe.
I would say that I believe that as well.
Yeah, and when you think about formation of life on our own planet, which is the only example we have right now, it happened actually really fast. The Earth is about 4.5 billion years old,
Mhm.
and life developed around 3.7 billion years ago. So there was less than a billion year period from when our planet formed to when the first examples of life happened. And you have to take into account that the first couple hundred million years of our planet's history, it was way too violent to support life. So it really does seem like that, at least on Earth, life formed almost overnight. As soon as the planet was able to support life, life formed.
Mhm. Yeah, and if it was extreme enough, it could have even while the Earth was that violent, it was setting up the building blocks for that beginning of life.
Oh, absolutely. Now, thinking about how life formed on the Earth, there are, of course, many theories about how that happened. The two most popular being the concept of it forming in tidal pools or in deep sea ocean vents. Now, we don't really know which one ended up happening. I think currently tidal pools is more supported, and it seems like that's more likely. But it could be the case that even if tidal pools are more likely, it just happened to form around deep sea ocean vents first, anyways. That's just how these things can work. But either way, those are two of the most popular theories for how life formed on Earth. And there are some other ideas like panspermia, which is the idea that life may have formed off of Earth and then have been transported onto the early Earth, either by being on asteroids or comets that touch down on the planet or some other means like that.
Yeah, which is definitely an idea that I also think could be possible because there are life forms that we know of right now that can survive in a vacuum for an infinite amount of time almost.
Yeah, exactly. And it is really funny to think about the fact that one of the most popular hypotheses for how life could have formed involves these deep sea thermal vents, considering that that is an extreme environment. We categorize the life that lives around these vents to be extremophiles.
Hmm.
And that is one of the supported theories of where life may have formed on even our planet.
Yeah. I mean, realistically, if you think about it, any of the first life in my mind would have had to been some kind of an extremophile because even though the earth was a lot less volatile when life first started forming, it still would have been nothing like what we're imagining life forming in nowadays. It would not have been a calm ocean or, a place where life can thrive normally the way that we think about it today.
No, that is absolutely true. A lot of the environment on Earth that life needs to survive only exists because life existed in the first place from the oxygen in our atmosphere. That was created by early life on Earth. That was actually anaerobic and oxygenated our entire planet as a byproduct.
Hmm.
And there was a large mass extinction event because of that. But, that's something we take for granted now. And it's a biomarker we look for life in general. Also, the stability of Earth's climate and temperature that is also in part regulated by these really long carbon cycles. So, yeah, you're absolutely right. The first life has to basically be a pioneer species, so to speak, and make this planet more habitable or make any planet more habitable so that following life forms can evolve in it and adapt to it and become more of a stable environment.
Yeah, it really is interesting to think about that. The first life would have formed in a much more aggressive climate, but yet it wants to thrive in a climate that is easier for it to maintain.
Yeah. Or, a lot of these extremophiles, they actually can't exist in the more mild climates there are now. Like, thermophiles that need to exist in environments of almost near boiling or in some cases above boiling. Some of these life forms have been found to exist at 120 C, which is well above the boiling point of water. If you go and plop them in a nice 70-degree environment, they'll die.
Yeah, yeah. I mean, that would be like ice plunging,
Yeah.
a normal person.
But yeah, no, I think it's really important to think about these extreme places that life can exist and how extremophiles on Earth can exist because otherwise we might be missing opportunities for life to exist. And just I want to touch on these a little bit before we dive into our extreme examples, just to show our audience that we're not just making stuff up. There's some basis in this.
Mhm.
There are, like I said, acetophiles. These exist in extremely acidic environments. I think they've been found in the negative pH range, which is more acidic than most concentrated strong acids that you can buy. I think even like concentrated HCl is only, a pH of near zero.
Yeah, so you think about something that can melt through most organic and inorganic compounds that we have, and that there's life living in it. That also combined with the fact that they're living in boiling temperatures is just crazy to think about.
Absolutely. A lot of these acetophiles have been found in hot springs and like volcanic environments where it's not just that it's acidic, it's also really hot, oftentimes near the boiling point of water. We also have radiotrophic life that we have found on Earth. There is a species of fungi that actually exists in Chernobyl near the melted down reactor, and it feeds on gamma radiation through melanin, the stuff that adds pigment to your skin, and it actually uses the gamma radiation and absorbs the melanin and uses that as a form of energy.
Yeah, that's wild. It's like a super extreme photosynthesis type of process. I mean, they're still taking in energy from a light source, just a very violent one.
Yeah, yeah, exactly. And it's crazy. There's no need for life to do that on Earth. There really is no need for it. But this is an environment that exists in a very limited place on this planet. And even though it exists in only a handful of places on our planet, we still see life adapting to it and evolving to it.
Yeah.
One of the other ones I just wanted to touch on was we found life that exists deep in the Earth's crust, as much as 2 miles down, where the temperatures regularly exceed the boiling point of water. They're around 120 C again, and the pressures are well over 1,000 atmospheres. And these life forms exist by metabolizing iron and hydrogen.
That's crazy to me. It really makes your mind wander on what could actually be out there, just thriving in these environments that we won't be able to see unless we dig deep to the ground of other planets.
Yeah, absolutely. Even life on Earth exists in some truly extreme and alien environments. And I would not be surprised to see life existing in even more extreme environments out there in the universe that we haven't even considered or looked for.
Yeah. I mean, there could be life close to us. Like we have gone to other planets before. Like we've gone to our moon and to Mars, but we haven't dug deep. There could be life there right now.
Yeah, absolutely. I mean, obviously, one of the most famous examples is going to be the oceans on Europa. People think that's a likely candidate for life, especially life existing in these deep sea thermal vents like how we have on Earth.
Hmm.
And the reason we think that can exist, or we had the idea that could exist, is because of the extremophiles we have found on Earth.
Yeah.
And that's a great example of us looking at what exists here and extrapolating that out to the wider solar system and hopefully the galaxy and universe beyond that.
Yeah. Crazy to think about.
So, speaking of crazy to think about, I think our first extreme environment definitely checks that box, which is that I want to envision how life could exist on a planet orbiting a black hole.
Man, that's such a crazy topic.
You made the joke in one of our last episodes that I always find a way to work in black holes. So,
Yeah.
you gave me the choice, and that's what I went with.
Hey, black holes are awesome.
Absolutely. So let's first talk about how you can actually have a planet orbiting a black hole. Because despite what Doctor Who has told us, yes, you can have stable orbits around black holes because they work like any other source of gravity.
Of course, it all just depends on the mass and your relative distance to that mass.
Yeah, absolutely. If we replaced the sun with a sun mass black hole, the orbits of the planets wouldn't change at all.
No.
Now, what would change would be the available energy for our planets, and which is to say there would be virtually none because black holes don't emit light.
Right.
So when we're talking about a planet orbiting a black hole, the first thing that comes to mind is what energy is going to power this life. And there really are two choices. Option A is that if you have a planet that has a more elliptical orbit, which is to say not perfectly round, but more of an oval where it passes closer and further away from the black hole, depending where it is in our orbit, then you will actually get tidal heating, where as the planet comes closer to the black hole, the tidal forces stretch it out. And then when it moves further away from the black hole, it returns to more of a brown shape. And this constant expanding and contracting of the planet causes the interior of the planet to become really warm and can provide it with geothermal activity. And that's similar to how we think that Europa can have liquid oceans because it goes through tidal heating with its orbit of Jupiter.
Yeah, that's such an interesting thought. It's almost like you're kickstarting the core of the planet every time that it rotates, allowing for it to, in some cases, for this extremophile life, could make it an even more stable and sustainable environment than some of our life has here on.
Oh, yeah, because you don't have any solar flares or any activity. They're probably going to be protected by a deep crust of ice that prevents any exterior influence like that. It would probably be actually quite a stable environment, like you were saying,
Yeah.
which is why that's actually not the case that we're going to be talking about in this example.
Okay.
Instead, we're going to go for an even more extreme case, which is that you could have a planet orbiting a black hole that has an accretion disk.
Okay.
So, an accretion disk is essentially just a disk of gases that, as they fall into the black hole and orbit the black hole, they reach relativistic speeds, high fractions of the speed of light, and collisions with these small particles release an immense amount of energy in the form of light and also in the ultraviolet up to gamma radiation range.
Yeah, which is something that can be more sustainable. And like with the fungi and the radioactive zones of Chernobyl, there could be plant or even animal life that has adapted to absorb that and turn it into energy.
Absolutely. And that's the case we're going to explore here. But there is, of course, a problem, which is that the accretion disks of a black hole emit most of their energy in the form of high energy radiation, gamma radiation. And while I think that life is quite adaptable and can handle a lot of extreme environments, realistically, a planet orbiting close enough to an accretion disk of a black hole would probably be bathed in too much gamma radiation to support any type of surface life.
Yeah.
However, we could imagine a situation where we have oceans on a planet orbiting the black hole, and the water itself will provide great shielding to this gamma radiation. Once you go down around 100 meters, you're going to have levels of background radiation comparable to what we have here on Earth.
Yeah, it would create a comfortable twilight zone within that range of the ocean that allows for life to form and live comfortably, even with that much hyperactive energy coming on to the planet.
Yeah, because while the surface of the planet would be a radioactive hellscape, once you're 100 meters or so below the water, it's not much different than Earth. And you brought up the term twilight zone, which is exactly about where this would happen at, because on Earth's oceans, around the 100-meter point, we have something called the twilight zone, which is where you do have a little bit of light reaching down through the surface, but it's mostly dark. And I think you would have that region on this planet being a fairly similar environment on Earth. I do think one key difference between a world orbiting a black hole and on Earth, at least in this twilight zone, is what's going to make up the basis of that food chain. Because if we're imagining life on this planet, anything that gets close enough to the surface of this water to use photosynthesis to harvest that light is probably going to be in too high of a radiation environment to exist.
Hmm.
Now, could life evolve and adapt to handle that level of gamma radiation? Maybe. I mean, we haven't seen anything that can handle that much gamma radiation here on Earth. There does seem to be an upper limit to how much radiation can be tolerated. So, in this example, we're going to assume that no, life can't handle the amount of radiation that would be entering the surfaces of these oceans, which means it's unlikely you would have photosynthesis taking place on these planets. In this environment, you would likely have these radiotrophic lives, like how we saw on Chernobyl, that exist maybe tens or so meters below the surface, too far down to harvest light energy, but that rely on radiosynthesis.
Yeah. But if that base can be established, then we have to assume that there will be life that will evolve to feed off of that base and can produce even more multicellular organisms that would do such a thing.
Absolutely. I think once you have any type of life that is supporting itself, predation happens naturally. You've got this life that can support itself by harvesting gamma radiation, and then it just seems like predation is going to be the next logical step. And you can even have single cellular predation of these, bacteria and stuff that harvest these other radiotropic lives.
Hmm. I mean, if the energy is there to take, life will take it.
Yeah, I
So
genuinely think so. Absolutely. There is a consequence to this, though, which is that without photosynthesis, using radiosynthesis, there's a good chance that they will not produce oxygen as a byproduct, which means the oceans of this planet are potentially going to be anaerobic in nature.
interesting. So that would mean that this life, although it would evolve in a similar way to how life here has on Earth, it would also have a lot of very large differences with what they can withstand just in their day to day.
Without aerobic respiration, there is going to be a lot less chemical energy available to these species because oxygen is such a great electron acceptor. Most life on Earth uses oxygen to drive our metabolisms forward, and that's something that would likely be missing from this planet. And that means there's going to be less energy available for these species because anaerobic pathways are just less efficient overall.
Right. So, how do you think that these types of life would make up for that lack of efficiency?
That's a great question. We do see multicellular anaerobic life here on Earth. I think there's even some worms that we've seen that are anaerobic. So we know that multicellular complex life can exist in these environments.
Hmm.
And I think that having such a large environment like this, you would see a lot of complex and large life, potentially even, comparable to what we see on Earth. However, the reduced energy availability could limit predation to an extent. You might see more species that rely on filter feeding and passive predation versus how we see on Earth, which is some aquatic species that rely on being fast and nimble. There just might not be enough energy available in these environments for that type of strategy.
Yeah. And with an environment like that, as we've seen in Earth's history, with less oxygen available, usually the species will be smaller, but more efficient. And
Absolutely.
as more oxygen is provided, they become a little bit less efficient, but they're able to focus on more things like strength or flight or size to be able to achieve other goals of life, like reproduction.
Yeah, absolutely. If you have an anaerobic environment like this, then every joule of energy really matters. You have to make every calorie count. And I think you're going to see, an even harsher evolutionary landscape on these planets than you would have on Earth because expelling a large amount of energy to try to catch your prey and missing could be life or death. You might only get one or two chances before you've expended all your energy.
Yeah. And it also makes you think of how long would this life last? Because usually when you think about things specifically extremophiles that live in these smaller environments, not only are they more suited to survive more efficiently, like we were saying, but they also live longer
Mhm.
on average, which is interesting to me.
Yeah, well, I mean, it makes sense because they have to take a slower path through life, slower replication, slower metabolisms. And this is true on Earth too. It's just anything that has a slower metabolism tends to leave longer. You get less replicative errors, less oxidative stress, or in this case, no oxidative stress. Overall, it just leads itself to longevity.
Yeah.
So, yeah, you might have these life forms living for a very long time and conserving their energy overall. And if we're imagining being in this environment, you might see a lot of more like jellyfish type species and filter feeders being the dominant form of life and maybe even the top of the food chain instead of how on Earth we have more predator driven species at the top of the food chain like sharks and tuna and stuff like that.
Yeah. Things that were able to use oxygen to their advantage and be able to expel that extra energy. Without that extra oxygen, it definitely makes sense that we would see these low level creatures on the food chain be the top of that.
Yeah, exactly. And filter feeders really might be the top of these food chains. So now, stepping away from a water world orbiting a black hole and going to, I guess, what on the surface seems to be a less extreme environment, but I think as we'll soon show, definitely is not, is we can talk about how life could exist orbiting a red dwarf star.
Yeah. Now, this one is really interesting because red dwarf stars are some of the most abundant stars in our universe,
I think they make up like 70% to 80% of all stars.
which is crazy because when we think about what life could be out there and we are actually able to expand our understanding of what life is and how it can form, then that makes the high probability of life being out there even higher.
Oh, absolutely. I mean, it could be the case that life is a lot less likely to form on a red dwarf star, but just the sheer abundance of them makes that type of life more common overall.
Yeah.
Now, it doesn't sound, I guess, like on the surface, like such an extreme environment, but it can be a little misleading because even though these stars are less energetic overall compared to our type of star, They tend to be more active. They have a lot more solar flares, and a lot of them are classified as flare stars. In fact, I think most red dwarf stars are classified as flare stars.
I mean, that makes sense. They are stars that are in their early cycles of life that are just starting to form and come into their own. So you usually will see with everything in our galaxy, when you are just starting to form out there, things are much more violent.
Yeah, that actually is a really big issue because as these stars settle down, their habitable zones move in. So the first billion years of the star's lifespan, the habitable zone is actually pushed much further away. So any planets that are going to be in its future habitable zone once it calms down are actually going to be baked by the star for over a billion years, which means they could lose their atmosphere or even turn into Venus-like planets. And any planets that are in their current habitable zone will not really have a ton of time for life to develop because once it calms down, that habitable zone will move inwards and these planets will now be too cold. That is a huge issue that we have with life, along with the fact that once the habitable zone does come back into the star, the habitable zone will be so close to the star that many planets within it are going to be tidally locked.
Yeah. Now, being tidally locked is a really, really interesting topic when you're thinking about life, because usually when a planet is tidally locked, you have two very big extremes, right? You have very hot and very cold on one side of the planet, very exposed to radiation on one side, and then none on the other. But either one could not sustain most life as we know it nowadays, but life will find a way, right? So you have to think there could be life that forms and it could live on the where the two zones meet. You give a habitable area, or there could be life that evolves to thrive in both those cold, arid zones on the planet or on the side of the planet that is being bombarded by radiation daily.
Yeah, exactly. And you mentioned there'll be this terminator of it's almost like a twilight zone. It'll be perpetually sunset, and it could have very modest and comparable temperatures that like what we find on Earth. The interesting thing is if you're imagining what it would be like standing on this planet, there's going to be a prevailing wind moving from one side of the planet to the other. As the hot air rises, it'll naturally move to the cold side of the planet where it'll condense, fall back down, and you'll have these huge planet-wide convection currents giving you a perpetual breeze of very strong wind. So whatever life we do have that forms on these planets is going to have to be able to anchor itself down.
Yeah. So when you think about it, really, plant life comes to mind for me on these planets, something that can root and anchor itself in very strongly, very sturdily onto the planet, and then be able to absorb the little bit amount of energy that is coming from its red dwarf star.
Yeah, because the red dwarf stars, they do emit less energy than our yellow dwarf star. And largely, though, they emit their energy in the infrared spectrum as well.
Yes. So when you think about a planet that's tidally locked and you think about the type of life that can exist on this planet, which would, again, in my mind, be some type of plant life, you'll find really sturdy, low to the ground, dark types of plants that have super large leaves, as we have now, that will allow for them to be able to absorb that energy and go through photosynthesis. But they'll be in these shades of black and red.
Yeah, so they can make use of all the light that they get available to them.
Absolutely.
Yeah, I could 100% see that. And there have been some planetary models that suggest that if these red dwarf planets have an atmosphere, the convection currents carrying the air from the hot side to the cold side could make the cold side warm enough to be somewhat habitable. You still might end up with mostly ice caps and ice worlds, but that could insulate an ocean enough to potentially have ocean based life. And there is a potential for ocean currents that could carry heated water near the terminator, maybe a little cross it back to the cold side and provide enough energy for even sub ocean
Yeah.
environments.
And that's really interesting that you bring it up now. And I haven't thought about that until just now, that if you have those small bits of liquid water that are being superheated on this equator, but not enough to where they dissipate like they are on the bright side of the planet, that would create violent currents
Yeah.
on the other side. And it would allow for that warm, life sustaining water to be able to flow very quickly underneath these ice caps
Yeah.
that have formed on the oceans on the dark side.
Absolutely. And all the models for these planets show you would have perpetual rain. If you did have liquid water, it would constantly be vaporizing as it reached the hot side of the planet and then coming back over to the cold side of the planet where it would condense. And there would be perpetual rains on these planets.
Realistically, if you have that energy, it could create perfect conditions for life to survive, even on the polar opposite side of where all that energy is coming from.
Yeah, very possible. That could provide an energy flux. But if you will, I would actually like to take a slightly different tact on how I could imagine life existing on these planets.
Okay.
So I mentioned a big issue with these planets is that the habitable zone is so close to these stars, they get tidally locked. Then there's a lot of solar flares. So being closer to the sun during a solar flare is obviously not a good thing. There's a risk that your atmosphere could be stripped. And a lot of these issues basically stem from the planet being too close to the star. Unfortunately, there's not much you can do about that because further away, it's just too cold for liquid water. That's why we have these habitable zones. But that's the key point, right? These habitable zones are based on the notion of where can liquid water exist around this star. But if we ease up on the requirement for liquid water, we can extend the habitable zone. So if we consider the possibility of methane-based life, which is life that instead of using water as a solvent, it actually uses methane as a solvent. It actually uses methane as a solvent. You could imagine there would actually be a second habitable zone further away from the star where you could have methane-based life existing.
Wow. That is an incredible thought. I know I've heard many times that methane can sustain life.
It's theorized to be able to.
Right. So, how would that look?
Yeah, so it's worth pointing out that we're still talking about carbon based life here. We're not talking about any extreme differences in biochemistry, silica based life, or even like platinum based life. No, so there's still going to be organic carbon based chemistry.
Right.
The only difference being its primary solvent is going to be methane based instead of water based.
Mhm.
So if we imagine this, one of the largest issues that comes up with methane as a solvent is that it is not as good of a solvent as water. We often call water a universal solvent, which makes it a very good tool for life because you can have all kinds of different chemistry happening within it. And
Right.
that's what our biology relies on extensively. So methane is not as good of a solvent as water, but it is still good enough for many organic molecules. So for methane, one big key difference is that it is a non-polar molecule. If you're not familiar with the term, a polar molecule is like water. It has a positive and negative end, and that makes it really good at dissolving different things. Methane doesn't really have any charge distribution, it has an equal charge density all around it. And so it's nonpolar and it can't dissolve as many things.
Right.
But it does mean that many things that aren't soluble in water are soluble in methane, things like hydrocarbons and also fats and lipids that aren't soluble in water are soluble in methane as well. So we might see a more lipid based biochemistry. For example, it's been theorized you could have polylipids that take the place of amino acids to make up proteins.
Interesting. So, you could use an entirely different building block, but still create the same angle that is that information transfer for life.
Yeah, exactly. And there's even this concept of azeotomes, which I hope I'm pronouncing right, which is a form of cell membrane that could exist in a methane based solvent that uses acrylonitrile as its basis instead of phospholipids. So in water based biology, we have a phospholipid bilayer that protects our cells. In methane based biochemistry, you could have these acrylonitrile based bilayers that protect their cells. So you could still have individual cells made out of these acrylonitrile bilayers that use lipid based proteins. And for energy storage, you could actually potentially have this methane based life form breaking down hydrocarbons as a source of energy, which is nice because hydrocarbons are a huge source of energy here on Earth. You know, it's what powers your car. Well, maybe
Mhm.
not your car, but it's what powers you have an electric car, but it's what powers my car, unfortunately. And the only thing is that you definitely do not want oxygen in such an environment.
Right, because then you have an explosive reaction.
Exactly. So
So,
it's funny though, if you could imagine one of these environments, oxygen itself would be flammable. It'd be literally the opposite of what we have on Earth. You know, everything on Earth is surrounded by oxygen, and you know you have hydrocarbons that are flammable. These environments would be the opposite. Everything is surrounded by hydrocarbons, so the oxygen would be flammable.
that's very interesting to think about. So, a byproduct of life on these planets then probably could not be oxygen, or I suppose it could because we do have biological life that creates methanes.
Yeah.
But it couldn't be in the same level that we create oxygen here on Earth because it would explode.
Yeah, so it's theorized that instead of using oxygen for their metabolisms, they might work by reducing compounds to gain energy. So instead of breaking bonds by oxidizing them, they would break these bonds of hydrocarbons by reducing them, which makes sense because they can use hydrogen to do that. And it's very likely this would be a hydrogen rich atmosphere.
So, is there any basis that we have as of right now that gives us an idea that this could be a possible way for life to form?
Potentially, yeah, actually, Saturn's moon Titan is actually a place that exists like this. It has a liquid methane oceans and it has a methane cycle instead of a water cycle, where you have a methane based atmosphere, you have methane rain, methane oceans. And one of the key compounds that have been found on Titan, in Titan's atmosphere, are the acrylonitrile compounds that I was telling you could make up these cell membranes.
Wow.
And some people have even proposed that that might be the main way these acrylonitrile compounds are made. Although some other people have pointed out there's probably some natural reason for why these are there that we just have not yet found.
Yeah, I mean, of course, there could be reason, but one of the reasons could be that there is methane-based life there.
Yeah, it is definitely not impossible. But I do want to point out one of the interesting things about this is that if it comes to be that methane based life is possible, which we aren't 100% sure if it is, but if it is possible, then it could be the case, though, that because red dwarf stars are the most common types of stars, and because they're the longest lived stars, that methane based life could potentially be the most abundant type of life in the universe. And we could actually be in the minority of life being water based.
Yeah, that is very interesting. And a lot of our science, especially when we look for other types of life out there, we do measurements based off of our life,
Yeah,
right? Water-based life forms. So how would we be able to determine or even try to determine if there's methane-based life?
it is tricky. And it's why it's so important to consider extremophiles and these types of environments, because you're right, we might not have ever considered this. So if you don't have, some scientists sitting around dreaming up ways that aliens could exist on crazy environments, you might not ever know to look for it. And like I said, it's possible this could be the dominant form of life in the universe. And if we're not looking for it, that could be the answer to why we've never found life because we just ruled out these planets.
Yeah, it is really wild to think that because our scope is so narrow, because we base it off of what we are and what we're made of, there could be life all around us. We're just not seeing it.
Yeah, it is potentially possible. Now, it is, I think, less likely to have these types of life forms exist for a lot of reasons. Red dwarf stars are still very unstable. Solar flares are still an issue. And, there's reasons to guess that this might not be the case. I don't want our audience to walk away from this thinking that 100% methane based life is the most dominant type. It's just, it's mostly pointing out that it is possible, if it's possible that this life could evolve around a red dwarf star because these stars are the most common and because they're so long lived, it is possible it's the dominant form.
Of course, we have no proof that this could be something that's happening, but it is definitely something that should be more acknowledged, especially within the scientific community that is looking for life on other stars.
It is certainly worth thinking about, I think.
Yeah.
So, moving away from life around the red dwarf star, though, let's talk about our final scenario that I wanted to talk about, which is how you could have life existing on a gas giant planet.
Yeah. You see gas giant life a lot in sci-fi movies, I feel like. These massive space creatures that feed off of the gases that flow and they're able to remain buoyant on these denser gaseous planets. Realistically, I don't think that that would be a way that it would form. I think it would be more like how life starts on most other planets as microscopic. It would need to start that way.
Well, it'd have to start that way, but I guess you could potentially have the end state of life being these massive creatures that are buoyant and float and feed through the gas to harvest micro, almost like wells.
Yeah.
Maybe they could be filter feeders and bring in the gas in the atmosphere and try to pull out microbes and eat those.
Yeah, yeah, I mean, it definitely could be, and they would be massive.
Potentially, I mean, these are big planets, so you have room to grow.
Yeah, they would be essentially like flying zeppelins, flying hunting zeppelins on these planets.
But you did mention about the formation of life on these gas giants, which might sound impossible, right? Even in the methane based example we just talked about, we imagine having some type of body of water or liquid of some sort for the biochemistry to happen. And that's kind of problematic when you're thinking about a gas giant because it's, by definition, a gaseous planet. There's no
Mm.
surface.
Nowhere for water or methane to pool.
Except, though, there are places where you could have water because there are regions on these gas giants where the temperature and pressure is correct to have liquid water, and it would exist in the form of water droplets or water vapor, much how it exists here on Earth.
That is very interesting to think about. So, water droplets that essentially just float in the atmosphere and they just stay there for years and years and years. If they're exposed to enough energy from their star, then there is no reason why they wouldn't be able to accumulate the stuff that they need to create life.
Absolutely. I mean, even on our gas giant, Jupiter, right? A lot of organic molecules have been found, including amino acids. And Carl Sagan actually wrote a paper about how life could exist on Jupiter. And he argued that the half life of many of these amino acids on Jupiter are comparable to how they were on Earth. They could last for hundreds to thousands of years before degrading. He also argued that the current atmospheric makeup of Jupiter is very similar to the atmospheric makeup of the primordial Earth.
So, if the primordial Earth is what produced life in the first place, it's only logical to think that the same possibility could happen on Jupiter.
Yeah, it is very possible. And actually, he took it a step further and argued that it's not only possible, but maybe even more probable because the surface area of Jupiter is so much larger than the Earth that statistically speaking, he said it might even be more likely to see life forming on gas giants. And he also made the argument that because you have the biochemistry happening in these suspended water droplets, you have a larger surface area for life to get started in.
It would definitely be more controlled. It is really cool to think about that you could have just these pockets of such different organisms living in each individual droplet that is surrounding a gas giant.
Well, you mentioned more controlled, and that is actually another point. I don't think Sagan brought this up in his paper, but if you are imagining these water droplets, one of the issues that we run into with life forming on Earth or any other planet is dilution. You need a decent concentration of these amino acids and building blocks of life to have life get started, like how we saw in the Urey Miller experiment, like the RNA world hypothesis. You need a base level concentration, and that's challenging to do on a water world because it all just gets diluted. That's
Mhm.
why we imagine life might have taken place in tidal pools because it provides a place where these molecules can accumulate. But if you imagine a gas giant inside of these water droplets, they're not going to be diluted. So they could potentially, as they're moving through the atmosphere, rising and falling on convection currents, absorb all of these organic molecules and build up the concentrations needed for life to get started.
Yeah, I mean, that makes a lot of sense. You do need that concentration because otherwise, I don't want to say life would see it as not worth it to produce themselves like in that environment. But if nothing is stable for long enough, then in my mind, life just would not function.
I mean, yeah, if you only have two amino acids bumping into each other once every 100 years, it's really hard to imagine that life is going to get formed in any reasonable amount of time.
Yeah. But when they have these controlled environments and they can do that, it definitely is feasible. Now, how long would these water droplets be able to survive? I know you said tens or hundreds of years. Do you think at that point that is enough time for life to really come into its own? Or do you think it's a cycle of life just popping in and popping out of existence?
Yeah, so the question isn't like if they get destroyed, is the life getting destroyed? The more or less the question is, will these amino acids be stable enough in the atmosphere of this planet to be able to be accumulated in water droplets and actually be susceptible for life? If the amino acids get destroyed too fast, then the concentrations would be too low for life to form.
Yeah.
So you need a certain half life of these materials so that it's around long enough and high enough concentrations for life to potentially utilize it. But you mentioned, would life be around long enough to form? And actually, Sagan touched on that a little bit in his paper because he posited that for any type of primordial life, of life that just got started, it's likely going to be denser than the surrounding air. And it will, over time, sink through the atmosphere until the pressures and temperatures are too high for it and it would be destroyed.
Right.
So he argued that if this was the case, if you had life that could exist on these planets, it would need to reproduce at such a rate to counteract that. So it would have to reproduce fast enough to account for how much of it gets destroyed, because a certain amount of its population will always be drifting too low down and be getting destroyed. You need a decently high rate of reproduction for life to exist on these planets and then stay existing, which might sound like an issue, but it's really not. It's very, very common on Earth. Phytoplankton and our own oceans run into the same problem. They are heavier than the water they exist in. They slowly sink in the ocean, and once they hit a certain point, they die because there's no longer any light for them. And the way they get around it is just it's nothing crazy. They reproduce fast enough to account for that.
Okay. So that is very interesting that, they produce and then they sink. Some of them die and they rise back up into areas where they can thrive again, almost like a life cycle,
Yeah.
right? But like we touched on earlier in the black hole, what if they produce slower?
Yeah, so, I think you can have slower reproducing life, and Sagan in his paper again also argued you could. He just argued that if you have slower reproducing life, it needs to be complicated enough to maintain buoyancy. So maybe you start off with single-celled life that just evolves really fast, but over time you could get multicellular life and even more complex forms of life that are able to maybe selectively capture hydrogen because that's the lightest element. So if it
Hmm.
could selectively capture hydrogen, it could become buoyant and lighter than its surroundings, and at which case it now doesn't have a clock of needs to reproduce fast enough to survive death. It can instead just remain buoyant and there's no loss of population due to sinking through the atmosphere.
I see. So when you go in the other direction, that's when you really start, getting these speculative space whales or space jellyfish.
Yeah, absolutely. And you could have stuff like that. There's no reason you couldn't have larger organisms that evolve to be filter feeders and exist within this atmosphere, like almost a well. It's very comparable to that.
Yeah, as long as they can pull in their building blocks from the atmosphere that they're in, that's super cool to think about.
Yeah, Sagan himself, and I think his co-author was Saltpeter, they postulated about the idea of life existing specifically on Jupiter. But one of the issues they ran into was that for Jupiter, the region where you can have liquid water is too far down in the atmosphere to receive any sunlight. So while you could have liquid water, you couldn't have photosynthesis. But if you want to imagine potentially a gas giant that exists closer to its host star, you could have the region that supports liquid water be higher up in the atmosphere and could also receive light from its host star and could support photosynthesis, which just makes life even more common on those types of gas giants.
I see. Yeah, so it would be like again, like a Goldilocks zone, but just for gases instead of liquids like
Yeah,
we see on our ocean.
very possible.
Yeah, man, that is wild to think about.
Well, that's all I have to say about life on the gas giant planets. I hope everyone enjoyed our three hypothetical situations where you could have life. I know I enjoyed thinking all these up. How about you?
Oh, yeah, absolutely. And all of these topics are so fascinating. As I was doing research through them, I definitely think that we could go back and really dive into all of these in later episodes.
Absolutely. I do want to make individual episodes touching on some of these. I particularly like the idea of underwater civilizations, which I know is what we'll be covering in our next episode.
Yeah.
So if you like that idea, come back for the next episode, not next week, but the week after.
All right. Yeah, that'll be exciting. And we'll be happy to see you guys there.
Take care.
Bye bye.